My name is Sarapnaz Karimi. I'm chairing this session. For the first talk, we have Jeffrey talking about tandem anchoring. Thank you.
So my name is Jeff Lund. I'm going to be talking about interactive topic modeling and our approach, which we call tandem anchoring. So very briefly, topic modeling is an approach which aims to discover latent topics in a large collection of documents. And when I say topic, what I mean is a distribution over words, typically a categorical distribution, but not necessarily. It's a distribution over the words of the vocabulary of our corpus. So for example, suppose I ran a topic model on a collection of Amazon product reviews. I might see topics something like this. We have a topic that seems to discuss cameras, and we represent it by remembering that topics are distributions, we represent it by the n most probable words in the distribution. So words like lens, camera, Canon, Nikon are associated highly with this camera topic. In contrast to traditional offline topic modeling, where it's sort of a take it or leave it sort of proposition, our goal is to include humans in the loop while we're inferring the topics. And that enables a wide variety of new use cases. We can customize the model for our particular needs. So maybe with this Amazon product review data set, we're not so much interested in the natural topics that come out that tend to be about product types. Maybe we're more interested in the number of ratings a particular review received. So we can guide the model, inject human domain knowledge into the model, and we can guide the model so that we see topics that relate more to product quality or product price. So this is a useful way to think about topic modeling, but it does introduce new requirements into the runtime, specifically around how long it takes for an update to take place. Cook and Thomas, who are HCI experts, they argue that for complex user-initiated actions, such as requesting the model update and display the update based on user feedback, they argue that updates like this should take under 10 seconds. And the reason for that is the cognitive load on the user. You can imagine giving your feedback in some UI, clicking update, and then having to wait a couple of minutes. When you come back, you'll have to reorient yourself to the application, remember exactly what you were trying to accomplish. And that load harms the interaction. On the other hand, if you click update and the model displays the new topics in a second or two, you can very easily continue where you left off, remember what you're doing, and continue interacting with the application. I want to note that while existing interactive topic modeling literature does allow for the injection of human knowledge, they don't actually meet this requirement of runtime. The state-of-the-art fast ITM by Hugh et al., even on a moderately sized data set, they're well over this 10-second benchmark. So what we're going to go after is a fast algorithm for topic modeling that enables true interactivity. For that, we're going to turn to the anchor words algorithm. And this is, rather than looking at topic modeling as a probabilistic problem, we look at it as non-negative matrix factorization. And under some assumptions of separability, which we'll discuss in a moment, they can provably recover the topics in polynomial time. So just a very brief overview of how this algorithm works. We first represent each word in our vocabulary as a point in vector space. This is a v-dimensional space where v is the number of the number of terms in our vocabulary. And each dimension corresponds to a probability of co-occurrence. So if this x-axis, I've only drawn two of the v dimensions. If this x-axis represents the word cat, the words on the right here, they have a high probability of co-occurring given that we've already seen the word cat. The next step is to then choose specific words, which we call anchor words. These words uniquely identify a topic, meaning that they have non-zero probability only in the topic which they anchor. So camera, for example, that's a word we assert. This word only occurs in the context of discussion about cameras. It cannot occur anywhere else. Typically, we discover this using a modified form of the Graham-Schmidt process, and we assume that these words have this separability assumption, namely that they're unique to topics. We then represent every non-anchor word as a linear combination of the anchor words. And this gives us the inverse conditioning that we're after. We want to know the probability of a word given a topic. The coefficients of these linear combinations gives us the probability of each topic given a word. But we can just use Bayes' rule with the marginals for each word, and we can recover the topic matrix we're after in the first place. So I know that's very fast. There's more details in Aurora's paper, but I do want to pull out this figure from their paper, which talks about scalability. The three figures, or the three lines on this figure labeled recover, are various methods of recovering this topic matrix using anchor words. And what you can see in this figure is that with respect to data set size, the runtimes appear almost constant. And the reason for that is because we scale with the size of the vocabulary, not with the number of unique token types. If you think about the algorithm we just described, we find one linear combination per word type. And at a certain point, adding new documents to our data set doesn't introduce new vocabulary terms. So compared to, say, LDA with Gibbs sampling or even stochastic variational inference, this algorithm is very scalable. So we have a very fast topic modeling algorithm. The question is, how do we actually interact with it? We want to do sort of the same thing that ITM did to LDA and find a way to hook in the user's intuition into the inference of the topics. Well, the obvious way to do that is to allow users to either directly or indirectly modify the anchor words themselves. But this turns out to be problematic. The reason why it's problematic is because the anchors themselves are fairly unintuitive due to the requirement that they need to be unique to a topic. If we don't have this quality, then they will break the assumption of separability, and so they won't work. But a proper anchor word which is unique to a topic is actually fairly difficult for humans to choose. We have here an example of a user trying to construct a topic that concerns camera bags. And intuitive words like camera or bag, they don't work. Camera, for example, talks about the topic anchored by the word camera, discusses cameras in general, and the topic anchored by the word bag talks about all sorts of different bags, including bags used in the Diaper Genie product. So if any parents out there, you know very well that this topic doesn't concern camera bags like we want. Turns out the anchor we need is backpack. Because in this particular set of reviews, backpack is only used in the context of camera bags, specifically the backpack-style camera bag. Had this been a different set of reviews, perhaps one that talks about school bags, we'd have to find a different anchor. So our solution is to allow users to form single anchors from multiple polysemous words. We named it inspired from a concept from boating, where you can use multiple anchors from a single boat and you can get more holding power. Our idea here is that we'll allow users to specify multiple words that maybe individually are not good anchors, but jointly they somehow represent a pattern that is useful for the concept they're trying to express. So going back to our backpack camera bag example, we will take the vectors for the individual terms of camera and bag, and we'll somehow combine them. And we'll choose a new point in space, which has expresses a unique co-occurrence pattern. This pattern doesn't correspond to any one word that's in our corpus, but we can still use it as an anchor, as it is just a point in space. There are some details in the paper that we go over how exactly to combine this. There's a lot of ways you could do it. You could even use something as simple as just vector average. That turns out not to be what you want to do because you need to account for polysemy. But like I said, more details in the paper. Think of this, though, as something along the lines of an average. We need to find a point that represents the combination of all the words in the anchor. And then what happens is this new point in space, while it doesn't correspond to a word, it does serve as an anchor, and we can find words that are related, find words that should be in this topic. It turns out that this method does work. Here we have the camera plus bag topic. This tandem anchor does seem to express a topic that is very similar to the backpack topic, but the anchor words that go into this tandem anchor are much more intuitive for a user. And then on runtime, we inherit the runtime from the original anchor words algorithm. On a slightly larger data set, we still run just over 2 seconds. And in fact, if we had increased the number of documents by, say, an order of magnitude, we would still expect to see a runtime about 2 to 3 seconds, because we're, unlike traditional topic modeling, model-based topic modeling, we scale with the size of the vocabulary. So we have this very fast topic modeling algorithm. We have a way to inject human knowledge into the model. The question is, is it actually usable by humans? Is it actually intuitive enough for humans to express topics and concepts that they're after? To answer this question, we designed a simple user study. We use the topics as features for a classification task, with the idea that if the humans are really able to express the concept that they see in the data, the topics should improve our accuracy. We might not achieve state-of-the-art accuracy, but we're interested in the trend. If we can improve the accuracy, then we can argue that the topics better reflect the underlying data and that the users are actually able to accomplish the task of improving the topics and moving the topics in a direction they wanted to. So we're going to compare topics created both by tandem anchors and single word anchors. As we mentioned earlier, there's no other interactive topic modeling algorithm that's actually interactive. So for our baseline, we used the automatically generated anchors using Gram-Schmidt. Very quickly, this is the interface that we presented to our users. On the left, the users are able to edit the anchor words. They can add and remove words as they see fit. We also have the ability for them to add entirely new topics or remove remove a topic entirely. This is a significant advantage over Hugh et al.'s ITM, which has a fixed number of topics. We found that users would vary quite a bit in how many topics they felt the data needed. Once they've made some edits, they can click Update Topics, and a second or two later, the updated topic words are displayed. So as I said, we use the topics, or we use the accuracy in a classification task as a proxy for how well the users were able to modify the topics to reflect the underlying data. As we can see, the topics produced by tandem anchors are superior classification features. We also measured various external clustering metrics, and the story is largely the same. One interesting thing we found was that topic coherence we achieved the same topic coherence using tandem anchors that we did with single word anchors, which is somewhat perplexing considering that we just claimed that tandem anchors produce better features. What this says is that if you look at the top n words of the topics produced by single word or tandem anchors, they do seem to express a concept that is coherent. So to kind of tease apart this riddle a little bit, we turn to some newer metrics that talk about topic significance. There's a variety of them in the paper, but the basic idea is that we measure the distance of the topic word distribution from some underlying background distribution. So for example, here we have the distance of the topic word distributions from the uniform distribution over words. And what we see is that tandem anchors produce topics which are far more significant, meaning that they are more specific. They may express a concept just as well, just as clearly as the concepts expressed by single word anchors, but they're more specific, where the single word anchors are more general. And indeed, if we compared the number of topics produced by tandem anchors, it was roughly twice as many topics when the users were using tandem anchors as when they did using single word anchors. So they were able to express very specific concepts that they felt that were actually in the data, whereas they were unable to do so with single word anchors. So in conclusion, tandem anchors are more intuitive than single word anchors. Users are actually able to use this to affect changes in a topic model, and therefore we're able to produce superior topics compared to our baseline. And most importantly, tandem anchors is the only interactive topic modeling algorithm that you can truly claim is interactive. Thank you. Right, over here.
This is neat stuff. One thing that really jumps out at me, though, is the fact that you're using unigrams only. And so camera bag is a noun-noun compound. You can imagine using something like carry camera as a verb-object combination, a syntactically mediated multi-word expression. And it seems to me that would also be a different way of addressing some of the issues that you're seeing. For example, those combinations disambiguate, and they're also much more likely to be more unique within a topic. Have you considered trying that? I don't see any reason you couldn't do both.
Yeah, that's a fair point. We have considered trying multiple word expressions or various collocations. We haven't actually done any of that. But I would note that there is no restriction that these words be bigrams. I chose an example like that just for illustrative purposes. But a lot of the anchors, the tandem anchors that users produced, there was no obvious phrase or collocation in the words they chose.
Pre-processed so that those things are actually features for the topic model, and that might actually help some of the problems you're having just using unigrams.
That's a fair point, yeah.
Thank you for the talk. I wonder whether it's possible to combine this approach and standard unsupervised approach, so some of the topics are not defined by the user but just pop up from the data.
So we do seed the interface with topics produced automatically by the Gram-Schmidt process from Aurora. But those are just single word anchors. We haven't done any work to actually produce multiple word anchors automatically. That's definitely something we're looking into though.
Thank you.